And then we will go into a hands-on workshop where I will code in front of you how we can do text analysis or text classification, or what you also say, sentiment analysis. So I will, at the end, I will close with this notebook. It's a Jupyter notebook where you can go at home, fiddle out with it, try it on other data, and see how it does. So let's first start with the introduction. The skills that you require today are pretty simple: basic linear algebra, very basic stuff. Also some probability theory. Knowledge of Python is needed, and access to Colab notebooks. But since you all have access to Google Meet, so access to Google Notebook is granted. So let's start. I will introduce a bit of NLP history and where are we positioning the workshop today. NLP can be traced back into 1950s with Alan Turing, if you heard of it, the famous British scientist that discovered, he made the Enigma machine and won the World War. Also, Alan Turing developed what is called the Turing tests, which is a method of determining whether or not a computer is capable of thinking like a human being. And how this works is by having a human questionnaire. So a human will sit in front of a computer, or technically in front of a wall, and on the other side of the wall there will be either a human or a computer. And after chatting with both the human and the computer without knowing which is who, the human will be asked if to classify or to name which was the computer and which was the human. If it failed, then the computer passed the Turing test. If the human also wasn't able to tell which is which, then also the computer will pass the Turing tests. The first like cited application of NLP was with the ELIZA chatbot. It's a very basic chatbot designed for psychological assessment. It's basically it like returns all your questions or all your statements as questions. So, for example, if you said like my head hurts, it will say, why do you say your head hurts? So it's pretty basic, but actually back then it managed to fool many people into thinking that, oh, this is smart, but it's actually like a parrot, a smart parrot. So in 1980s, people started using machine learning for algorithms for natural language processing, and these machine learning algorithms are statistical machine learning. So basically, they're counting the recurrence of words in text, frequencies, and this basic stuff. I'll touch on it in a few more slides. And today, the workshop will mainly tackle the 2013. If you see, like there is like a gap between 1980s and 2013. It's like the winter of AI, the winter of NLP. Nobody touched on NLP until in 2013. The people introduced word embeddings, which I will focus a lot on today. And they adapted neural networks for natural language processing. So neural networks was, I think, introduced in 2010s, and they adapted it, made it better work for NLP in 2013. And the more advanced stuff, which I won't be able to cover today, are what's called sequence-to-sequence models that are used in like translation, because the input is a sequence and the output is another sequence, but both are text. And later on in 2015, you see like here the inventions or the critical inventions were year after year. So it's a summer of NLP. And then in 2015, someone introduced what is called the attention mechanism. It's also pretty advanced. And lately, if some of you heard about Google releasing something called BERT, B-E-R-T, it's a pre-trained language models around. Based on the transformers architecture, and nowadays everything is transformers. So I can say that transformers like replaced the thing that we'll be talking about today, but transformers are hard to use. So the things that I talk about today are pretty much still relevant. So you can go and use them in production, in your research, everywhere, and they're still relevant. So I will also introduce you to the NLP workflow. It's a basic like a map on what to do before starting or during a project. The first thing that you should always do in NLP is like look at the text, perform some data analysis on the text, see what is like the distribution of words, what are the common issues, what does the text contain, like get a feel on the text. So text processing and data analysis come first, and then we need to somehow represent this text into numbers. The old ways were to just like count the text and count the number of words in a sentence. I will touch a bit on it. And then the new ways are called word embeddings. So today our focus will be on text representation here. Let me get the laser pointer. So we'll focus around text representation. And then after representing text into numbers, we'll move into model selection. So we have to choose which model to use, which architecture to use. Today I'll introduce two new architectures, like the neural network and call it recurrent neural network, which is designed for text especially. And at the end, data engineers or data analysis or machine learning engineers will have to think about how to deploy their models. Evaluate usually comes with model selection, but it also we should always evaluate our model during the deployment. So even when we deploy in production, we should always evaluate if the model is performing good because of like a drift in the data, we call it. This is pretty much a bit more advanced than our topics today. So yeah, let's start. You remember in 1980s, the machine learning algorithms, they are TF-IDF, or what's called the traditional word vectors. They are also called bag of words. Why bag of words? Because to form a vector, we just count the occurrences of a word in this vector. So let's say our vocabulary is composed of about like 100,000 words. And we take this sentence, let's say it's called "It's a puppy." And our vocabulary it is a puppy, cat, pen, A and S. This is a very small vocabulary, let's say. So to transform the sentence, we just count if the word "it" exists, yet it exists, yes it exists, and is and puppy and A exists. So our vector will be 1, 1, 1, 2 zeros, 1 and 0. This is a representation for the sentence "It is a puppy." It's a pretty basic representation, pretty dumb if you ask me, but this is how it started. Like even if a word occurs twice, like the word "is" here, it occurs twice. But and then people moved into a slightly better representation, which is called the TF-IDF, term frequency inverse document frequency. I'm passing fast over this because these are the old ways, and I'm not focusing on it much. This is where we need to account for common words. So like the word "is" here is pretty common. So it's like useless to include it in a representation. Is and A, these are like, it's called stop words, which are pretty common in language, but they add very little value in terms of understanding like the topic of the sentence. So we need a way to filter them out. The way to do it is by dividing by the inverse document frequency, which is dividing by the how much frequent these words are in the whole corpus that we have, in the whole data that we have. So like the word "I" here is very common, so the denominator will be huge. And when we when we do term frequency and inverse document frequency, so when we divide the term frequency by the inverse document frequency, we get a very low score. On the other hand, like love here is not very common. This is an example again. So love here has a much bigger value than I, so it has a higher score. And this is how like traditional TF-IDF works. A big limitation of TF-IDF, if you can see here, is word order. So order is lost because if I give you this vector, you won't be able to know what is the word. Did I say "I love dogs," or did I say "I love cats but I hate dogs," or did I say "I love dogs but I hate cats"? Because these will have the same representation. So any word order is lost. This is one of the problems. The other problem is that let's take for example English. English contains about 30 million words given all the variation on it, like adding less at the end, adverbs, adjectives. There are about 30 million words. In Arabic, it's even worse. In Arabic, we have the diacritics, tashkil, fatha, dammi, kasra. These are characters, and they add even more variations. So we're touching like each vector will be 30 million size, and most of it is zero. So it's pretty bad. We need a better way to do it. And this is where word embeddings come. Word embeddings aim to reduce this vector from like 30 million size, from size of 30 million to a size of 100, 300, 700, 1,000, whatever. But it's a pretty much small compared to the actual length of the TF-IDF vector. So enter word embeddings. So as I said, word embeddings are also vectors of real numbers. So these vectors carry semantic meanings. You'll see in a bit in a graph how do they carry them. So they are designed to carry similar semantic meanings. So each two vectors with similar scores should carry similar meaning. Now you'll see a bit what I'm talking. Again, these vectors are called low-dimensional or more dense representation compared with TF-IDF vectors, which are sparser or high-dimensional. Because we don't have to include all the vocabulary in them. You'll see now. So a 2D representation of these vectors is, or a 2D projections of these vectors using, if you're familiar with it, PCA, principal component analysis. You see that after we get those vectors, and how we get them, I'm going to touch on it in a bit. After we train and we get those vectors, we can see that like clusters of words that are grouped together, and these words like have some relation between them. So you can see like animals such as dog, cats, pets are all like grouped in a similar in a small cluster. Like push and talk, listen are also grouped in a cluster. And some people actually performed some actually could extract some synonyms like cars and autos are also in the same cluster. Antonyms, agree and disagree, because agree and disagree appear almost the same in the same context. So the context of agree and disagree is the same. They appear with the surrounding text is the same. So they must have very similar representation. You can also see scales like hot, warm, and cold appear in the same, also very close together in the same cluster. Hyponyms, which are types of relationships, like the relationship between a car, a truck, dogs, and pets, also appear in the same cluster. Context, I touched on those. Names, even names like Sam, Bob, first names appear in the same cluster. So this was a very powerful thing that we have, which is like grouping words into clusters, and then we can extract information from these clusters. Again, I'll touch on it in a bit. So how can we use these? Clusters? So if you're familiar with math, if you want to get how similar two vectors are, we can compare their cosine similarity. So if let's say we have one vector here and the other vector here, to just compare how similar are they, just get the cosine of the angle between them, which is called the cosine similarity. If you want to do it, you just multiply the dot product between the two vectors divided by their norm. Again, I'm not getting into a lot into math here. So again, the word embeddings have created groups of related words. We can use these groups to extract more features for, let's say, sentiment analysis. Later on, our case study will be on sentiment analysis. We'll see how we'll benefit from these groups, and that's how we use them in Fitchika, and that's how we develop our features for the text classification. And also, some people used it for other types of natural language processing tasks, such as part of speech tagging and named entity recognition, which is like recognizing, is this a name, is this a location, is this a organization, is this a, I don't know, time. You think that these are like trivial stuff, but they're trust me, they're pretty hard to figure out on a large scale, because like words can occur in different contexts with having different meanings, even the same word. Again, I have a beautiful visualization that I want to show you. If you want, you can go to the. The 3D visualization of the word embeddings. So here we see word embeddings from a category called word to vec. Word to vec are a bunch of pre-trained word embeddings. They are trained, I think, on, if I'm not mistaken, on Google News. So it's a large corpus of like 300 million sentences. And now we're downloading only 10,000 of them, and we'll see how the 10,000 will be clustered. So now we're performing the PCA. The PCA doesn't group them much. So here you can see, get some words. Okay, bass and guitar are very close to each other, but we can apply better algorithms than PCA. There is one called the TSNE, and TSNE will be able to group them even better. And you see, like, it's like magic, trust me. If you have any questions while it's loading, you go ahead and ask me. Yeah, to start, it's like we can call it training, but you'll see like now clusters forming, and each cluster will contain a subgroup of words. I'm rotating them, but it's taking a bit of time. They started deforming now. I think this cluster here is country names. Yep, Ukraine, Slovakia, Bosnia. And these are, remember, these are the vectors of size 200. So, and we're compressing them into a size of 3 using the TSNE algorithm. But this is just for visualization. Usually we want to use the whole dimensions. Check massage. Should branch out a bit. That should be a branch. Let's see the branch here. I think this is it's branching again. I will stop when it gets a bit more stable. When we can see actually structures. See one here. Like here is like a chemistry one: proton, neutron, ions, RNA, atoms, electrons, bonds. Here is one epsilon, phi, sigma. These are like math stuff. Here's a cluster. Doesn't, didn't, isn't, wasn't. So I think you get the point. Let's stop it. And we can now like zoom in on some clusters. This is like, oh, this is the first names. Keith, Kevin, John, Craig. We have here flute, cello, orchestra, percussions. And we slightly like go to another one, to another cluster, from rock, sonata, folk, to harp, chords, tune, tone. And if we leave it more, it will be, the cluster will be more defined. So now I stop it because I'm running out of time, honestly. So yeah, these are like word embeddings vectors. This is how we can visually represent them, just for us to understand if they what information they are carrying. Okay. So here, like, there is a one cluster for computer applications. It has Windows, Microsoft, and also filter by each word and get the most similar word to it. So the most similar word to Windows is Microsoft OS, Linux. You can do pretty much everything that is related to words on this word discovery or word analysis on this website. So the question now that I think you all have is how are we getting these vectors? How are we training them? How are we designing them? Who's coding them? Who's giving them value? So for that, I will have to go into neural networks and how neural networks work. It's a small introduction, a brief introduction on how this black box works. I will not get too much into it, but okay, I will get into details, but not too much mathematically. So you can think of a neural network as, let's say, for classification. So it's like a box, a black box here, that you have to input to it data and labels, and the box will spit out rules. So instead of going to a human and telling the human or developer, please write some rules for to, I don't know, to analyze this text. So مثلا, if you want to do sentiment analysis, and the developer will sit as a computer, and then they will start writing. If the word good is in the is in this tweet, let's say, it's positive. If the word happy is in this tweet, then it's positive. And okay, then you have to worry about negation. I'm not happy. Okay, that's another set of rules. And then maybe some ambiguous words, maybe some sarcasm. So these are like an enormous number of rules to write, and nobody can like sit and write them all together. And this is a very tedious job. So we export this job to a neural network. The neural network model will handle writing these rules. Of course, it will not write them if else conditions. It will write them mathematically, abstractly. And I will see how. So the function of the neural network model is like a function. We call it here, let's call it f, that takes as input the data and labels and spit out rules. This should be labels here. So it takes as input data and labels and spit out rules. The most basic component of a neural network is the neuron. The neuron, it's called the neuron because it was designed after the human brain, the neurons in our brain. It looks like it, but I'm not sure if it performs like it, because the neuron is, I think, it's much more advanced than this green blob here. So how does this blob works? So it depends on, think of it as like we have three inputs, and whenever the combination of these three inputs carry a high output, this neuron will fire. So it will output something, it will fire here. It will output some high value. And if the combination of inputs here doesn't make sense, it will output nothing. So this is very similar to how the neuron in the brain will work. So how does it exactly work? We have, like, let's say three inputs, x0, x1, and x2. And each input will have, on each input will have a weight. A weight is like a variable, a, b, c, or w0, w1, w2. And these weights, to get the output, we just take x0 times w0 plus x1 times w1 plus x2 times w2. And we get them into the neuron. It's a linear combination of the inputs and of the weights for the more mathematically relaxed people. We take this the linear combination of the inputs and the weights, and we feed them into an activation function. An activation function is basically like, you can think about it as like a threshold function. If the output is higher than 1, then output 1, let's say. This is one activation function. We have more complicated ones, but this is a very simple one that I think that neural networks started using back in the days. So okay, again, another way to think about it mathematically, it's the dot product between the inputs and the weights. So if you have the input, here we have one neuron. Next slide we'll see how can we combine all this neuron to form a network, which is here. Here we have 4 neurons, and whenever we combine neurons horizontally or vertically, we call them a layer. So here we have one layer in the middle. We have the input layer in red and the output layer. So let's start by the first neuron here. The first neuron will take the input, multiply it by some weight, and then add it to another input, multiplied by another weight, and then we have here an activation function, and then it will output. And then at the output, we'll just add all these. So how the thing? Okay, this is called a feed-forward neural network, or sometimes called a linear layer. Linear layer because here the relationships here are all linear. So we don't have tangents. We don't have non-linear transformation. Okay, I'm getting a bit more into math. So when we say we are learning, our algorithm is learning, or we are training a neural network. So what are we training here? What are we training are the weights. The weights here on the, see that the weights here are growing, represented by the width of this line. So we are learning these weights. And how we learn them? We learn them by doing an algorithm called backpropagation. Basically, backpropagation, it is it's a synonym of AI. Everyone uses backpropagation. It's the most, not the only one, the most popular one, a very popular one. So how we do it? We first, let's start by doing what's called a forward pass. A forward pass is when we take the input, feed it to the network, multiply by the weights, get an output, multiply the outputs here by some weights, and add. So we have one weight, we have a weight matrix here, and we have another weight matrix here, which is the W's, and the input is X. And we have a bias just to not have zeros everywhere, and everything will crash. So we have some inputs, we feed them into this neural network, and then we get some outputs, just like the equation here. We have an input X, we feed it to the neural network, so we multiply it by W's, which is the weight matrix, and then we add a small bias, and this is the neural network, and we get an output. Now this output, if when we start, we have a random initialization, so all these weights are randomly initialized. And how are we learning? We're just comparing our output to the actual output that we need. So imagine here, like if I'm doing, let's say, sentiment analysis, or I'm doing like an approximation or a regression task, like predicting stock markets, let's say. So my inputs are all the data, and the output will be a single number. So when I get this single number the first time, it will be wrong. And how I'm measuring this, how wrong it is, I'm just subtracting it from the actual number that I want, which is the label. So whenever I subtract the error from the actual the resulting here, the y, from the label, which is called y hat, we call it y hat or y prime, and this is how I'm calculating my loss. This is one way to calculate the loss. So this is the easiest way. Another way is if you've heard of it, least me sorry you square them, and then you subtract them, and then you square, so that you don't get negative canceling the positives. You just add up the errors. So whenever you get this error here of on all the data set, so you have to calculate it for the first entry, the second entry, third entry, and then you accumulate these losses. It's called the loss here. So the loss again is the difference between the output generated by the network and the true output. And whenever we get this loss, we have to backpropagate it using the backpropagation algorithm, which is written here. The backpropagation algorithm, how it works, it takes the old weights. So let's say I'm working with the weight here. And then we subtract from it the derivative, the partial derivative of the error with respect to this weight. So it's like we're saying how much are we have to adjust this weight so we can have a better output. If this makes sense for you. This is very simplified. So how much this weight should be adjusted so we are closer to the actual number of the output here, so that y is better. So this is how we get our new weight. And by how much? So like imagine if you're going into it's like a valley, and you want to get in to the bottom of the valley, which think of it as like the bottom of your loss. So your loss function is like this valley, and you want to get to the bottom of this valley. And at each time you take a small step toward the greatest descent. So the greatest descent angle. So you just look at your feet and say, here I'm this is the steepest step I can take, and you take it. And how large is your step is the learning rate. So maybe your step is 1 meter, maybe your step is 10 meters if you're the giant, maybe your step is a centimeter. So this is called the learning rate. And how does this affect us? So let's say you ended up at the bottom of this valley, and when you're there, you're taking a step of 10 meters. So you keep oscillating on top of the error, on top of the bottom. You will never reach the bottom because your step is too big. So this is where some learning rate scheduling and manipulation will happen, but we don't have to worry about it today. Just understand what does learning rate mean and how is this error calculated, and then what is back propagation. So that each weight is adjusted by the derivative of the error with respect to the weight, such that the output is lower, the error is lower than the previous error. So we're closer to the actual output. I know this is a lot for you to take, but if you have any questions, please ask me now here. Okay, no questions? We won't have to do this manually. So I will not go into coding the mathematical way to do this. There are Python libraries, Python frameworks that already do this for us, already perform this derivative for us, AutoGrad they call. Then we have the TensorFlow, the Keras, the PyTorch. These are three popular libraries that will do all this for us. We just feed in the data, select a loss function, literally just select it in text, and then it will perform everything. Set the learning rate, and it will perform everything for us. So why did I start with the neural networks now? Because they are needed to learn these word embeddings. And the first type of word embeddings are called the word to vec, which is like transforming it from a word to a vector. Word to vec were a bunch of algorithms, is an algorithm that was created by a team of researchers led by Thomas Mikolov from Google in 2013. So Google started actually with this rise in NLP, and if you look a bit into the future, you'll see that Google very much influenced every part of NLP, even until now. So what is the word to vec? Word to vec is a simple one layer neural network. So it's the same as this. It generates a word embedding given a word. So you give it a word, it will generate a vector. Like a man will be this vector, a vector of real numbers, and the woman will be a vector of also a real numbers. The good thing in word to vec or in word embeddings in general is that you can perform what is called math on them, or operations. So we saw the distance operation. We can also perform the add operation and the minus operation. So you can see that if we subtract man from a king and then add a woman, we'll get queen. So how, if we subtract the man vector from the king vector and then we add the woman vector, the most similar vector to the resultant vector is the vector called the vector of the word queen. And you'll see how we can do this in a bit. So how are these what data we use to train these vectors? These vectors are trained.
Question,
Yes.
please.
Yes.
How do you on the man? How do you decide the vector that would you select for a man or a woman? Because there are a lot of different numbers.
Yeah, I'll touch a bit. I'll touch on that in like 5 minutes.
Okay.
I'm getting into that. So we need training data. And where can we get training data? Just need free text, like large text corpuses like Wikipedia, news articles, whatever text we have, digital text we can get our hands on, the better. So the larger, the better. The objective of word to vec is that vectors that occur in the same context will have similar representation. So a vector, the vector kid and the vector child, because they can occur in the same context within the same sentence, they should have a very very similar representation to each other. Basically, they are interchangeable. So the more interchangeable they are, the closer the representation. And there is one famous quote by Mr. Firth, I think his first name is George, I forgot, is you shall know a word by the company it keeps. So that's the main idea behind word embeddings. We are so these numbers, we're learning them by by optimizing all the vectors. Hello, we'll see how I'm throwing a lot of words, but we're optimizing the vectors of all words, such as similar words will have similar vectors. So how we do that? There are two algorithms to do that. One is called continuous bag of words, and one is called scriptogram. I'll start with the continuous bag of words because it's easier to understand. So let's say we have the sentence here: the quick brown fox jumps over the lazy dog. But to train the model, we actually hide this word here. We just remove it, and we tell the model, please predict jumps. Please predict what is the word here. So the first time it will predict this word, it will make an error. The second time it might be, it will predict maybe a more sensible word. The third time or the nth time, it will start predicting jump or predicting even words that are more similar to jump. On the other hand, the other algorithm called the scriptogram is we give it one word and we tell it to generate the all other words, and the words on the left and the right. Again, I get a more detailed example. So let's say I have, now we're talking with vectors. Okay, let's say I have the sentence, I like playing football with my friends. So we want to predict the center word here. And this is how we create our training data. We take a window. Here our window is of size 5. Because, okay, here 3, but it should be 5. Because we're starting at the beginning, we want to predict the word I. We give it 2 words on its right because we have no left here. We can just throw zeros or padding. Just you can ignore it for now. And we tell it to predict the word I. And then this is one training example. The other training example, we slide this window onto the right by 1 token. And we tell it to predict the word like, given that I playing and football. We slide the window another time and tell it to predict the word playing, given that we have I like football with. And this window size is the parameter that we control. We can tell it to predict 10, 8, 7, 5. It depends on how much powerful computer, the compute that we have, the hardware that we have. So we have to predict the center word given the context words here. So the center word is the one wherever we had the one, and the context word is wherever we have is a bunch of vectors with ones in the word selected. Hello, you see what are these vectors here? Do you see them here? Okay, I think explaining them here is better. So we start by getting a vector where we have all zeros except 1 in the place of the word playing. So if the word playing here, okay, if I have the words I like playing football with my friends in each cell, the word playing or the word here, I think this is the word, it's the word like here. The word like, we put the 1 underneath it and everything else is 0. So we have one long vector with all zeros except 1 in the place of the word like. So this is one of our inputs. The second input is a vector where it's all zeros except 1 in the place of the word playing. So let's say here we have 100,000 words. So we put only 1. So we have a vector of size 100,000, and we have only 1, the number 1 in the index of the word playing. And we take this vector. This is the 1 hot input vector. So it's called 1 hot input or n hot input, wherever we have ones in the place of wherever we have words. It's like the bag of words. So here the word I imagine football like, okay, we have the words I image football like playing and with. But the first sentence here, I like playing, only has the word I, like, and football. I think this is another example, but bear with me. I think this is the 4th example. So we have the word I like football, and you want to predict the word playing, which is in the middle. I think, okay, I'm working with this example. So, and I want to predict the word playing. So I take this whole input vector, which is by the size, vocabulary size. You take a pen. I think it's easier with the pen. So here I will have a matrix. Oh, okay. Let's start here. I have a vector here of size, our vocabulary size. Okay. Our vocabulary size is, let's say, 60,000 words. So this is 60K. And then I have here my hidden layer, or the neurons that we learned about. Let's say we have 300 of them. Good. So my input will be this whole vector, 60,000 vector, and the output, and then I will feed it into this 300, and then the output will be, because I have to select one word out of 60,000, so the output here will be a vector of 60K. And I have to place one, so the model will have to place one in the box where we have the word playing. Again, the input is a vector where I have where I have ones in the places where I have the words I and like and football and with. So whenever I have the word like I have a one here. I have a one on top of football, one in the cell of the word like, and one in the place of the cell of with. So this is my input vector 60, and now each cell here is connected with all these. So each cell was connected like this. So each one has a weight. It has a each one of those neurons here is connected to every input here. I don't know if you get me. So let's say if every neuron, okay, this is the first neuron. This is the first neuron here, is connected to 60,000 neurons, and on each connection we have a weight. So we have a vector of 60K. And the second neuron also have a vector of weights of size 60K. The third neuron, same thing. So we end up having a matrix of size 300 by 60K. Got me? This is understandable here? So this is the first matrix that we have. The second matrix is the inverse of it. Why? Because each output here is connected to all the inputs. So each one, this is like, this is one output, is connected to 300 inputs. So this is, let's start, let me erase this a bit. So this is a vector of 300 just for this output. And this is another vector of 300, another vector of 300. We have 60K of them. And we have 300 here. So the first matrix, weight matrix, is of size vocabulary, of size embedding size by vocabulary size. You can transpose whatever. But you have two set of matrices that are transpose of each other in terms of the dimensions, but they have different weights. And then the model just has to predict to place a one, like here, place a one or place a one wherever we have the word playing. It just has to predict one here, and it has also to predict zeros everywhere. So in reality, this won't be it won't be able to predict actually zero. So it like predict 0.1, or it will be predict probabilities here. So 0.1, 0.01, and the one with the highest probability should be playing. So we encourage the model to predict the highest probability for the word playing. Maybe other words are also viable, but we want the word playing for now. So right now you're telling me, okay, Wissam, where's this word embeddings that you're talking about? How can we extract that? It's easy. You take the input layer here.
Question.
The input layer, yes.
How do you get the weight of the matrix? How did you come up with 300?
I set it from my mind. It's usually between 100 and 1000.
Oh,
It's just, yeah, you choose, you sit and you choose how much computer hardware I have, how much time I have. I have infinite, I don't know. Google had, I think, 20 days. They said, okay, we want, I think they built two set of vectors. One was size 100 and one was size 300. Why these two numbers? Just they chose that. Maybe this 400 was better, they chose 300. It's like a hyperparameter that someone needs to choose. If you have infinite power, you can try all the parameters, which is called a hyperparameter search, and then you can figure out which is the best. But this is very computationally heavy. So imagine if you have to try 300 times or 1,000 times, and each trial will take 20 days. See you in 2050. So how are we generating these word embeddings, or how we're getting these word vectors from the input? Actually, we want to take the input matrix here. Remember this matrix? The vocabulary size by embedding size. Vocabulary size by embedding size. And it's a size of, okay, it's written here. Size of 60K, here is 10K, by 300. So the word vector for the first word is this one. So if I say, like, I have a word, the first word here was I, the vector of it will be this vector here, this weight here. Because why? Because you can think about it, it's like I'm transforming I into a set of values of size 300. So this is my word vector for the first word. And then I take these word vectors and I go play with them. So you understand how we train them? Yes, no?
yes.
Not like, okay, not like 100% understanding. There are a few stuff that I didn't cover here, but it's like the idea is here. So we want the neural network to predict the missing word, and by doing that, the neural network will learn that the association between this word and the context word, and hence the weight matrix will be representing the semantic meaning of each word, or the meaning of each word, just by doing that. So now that we have our word vectors,
How did you say you come up with the 60,000, not the 300? How do you come up with
okay,
the 60,000?
again, you can okay, like scan. You can start by like scanning your text corpus here, Wikipedia, and let's say Wikipedia has 1 million words, and you choose that I want the 60,000 most frequent ones. That's, again, it's a choice. People usually do 1 million, maybe 2 millions, but you cannot go larger, because then you'll find only one example of this word, and you'll understand nothing from it. So what they usually do is like select a large number, maybe 100,000, 200,000, and then every other word will be labeled as unknown. No, like we'll tell the model, go figure it out. I won't tell you what this word is. It's an unknown word, and figure out what the meaning is, because we cannot cover all the words using this algorithm. That's a limitation of it. So we have to choose a large number. So this is why when the more text you have, the larger or the better the representation that you have. Okay, sorry if you're hearing white noise, but waiting for the generator to come back. Okay, to play with these word vectors, there's a library called Jensen. And Jensen allows you to easily download the vectors and start directly playing with them. So you can use this code here. You download the word2vec from Google News. It's a 300 of size 300. And you can say like print the most similar word to Paris. Here the most similar word to Paris, using the cosine similarity, is Louvre, Venice, Vienna, whatever this is. Also, you can perform like this math that I talked about, can provide the positive examples here and the negative examples here. So you say everything here is positive, everything here is negative. Just like here, the king is positive, the woman is positive, the man is negative. And then the function will perform this similarity search, and it will throw to you queen, which was the most similar to the output. Yeah, the output here is most similar to queen, or throne, or Elizabeth. I don't know. Elizabeth was maybe associated a lot with queens and thrones and kings and men. But you get the point, I think. There are other types of word embeddings, more advanced types of word embeddings that let's see. Okay, I won't cover them a lot. That have tweaked a bit this algorithm. Maybe I won't cover them. I leave them in the slides. It's the slides that you have them, but I want to focus more on Arabic word embeddings. If you want to use Arabic word embeddings, we have those. It was the recent one's called Aravec 3.0. It's trained on Arabic Wikipedia, okay, Arabic Wikipedia only. I'm not sure if you use articles. And they have one trained on tweets. I think it's 1 billion tweets or 200 million tweets. So it learns dialects. They have Mazajak embeddings trained on a few million tweets. They all have size, I think 300 or yeah, I think they have size 300. And we have Arabic fast text from Facebook, which are the fast text embeddings. I won't go into those because we're running out of time. So the limitation of this approach, or limitation of the IDF that we solved until now, we represented the meaning by the context. Okay, we did it, and we reduced the size of the vector from 30 million to 300. Which, okay, we solved the first. Sorry, we have solved the first two issues. We still have one issue left, which is the order information, because right now in the embeddings, order information is still lost because the network doesn't care. So how will be solving this issue of word order information? To capture the order of the words, we have to consider. Okay, let's consider the task of text generation. So I say today the weather is gorgeous, and I see a beautiful blue, and I think most of you will answer sky here because sky is pretty much associated with the whole the context of this sentence here. This is also it's a task of training word embeddings, predict the next word instead of predicting the middle word. But how can we make this neural network model read from left to right? We want it to read like a human read from left to right. So how can we do that with neural networks? We want something called recurrent neural networks that can work on sequential data. So time information, we want to incorporate it in this neural network. So how can we do that? Let me start by the Fibonacci sequence. I think most of you know it. So to calculate the Fibonacci sequence, you start by two numbers, and then the third number is the addition of the previous two numbers. Okay, easy. Then the fourth number, the addition of the two previous numbers. So whenever I have an output, I feed it back into the input as an input. So 1 plus 2 is a 3, and then 2 plus the output is 5, 3 plus the output is 8. So this is like a recurrency here. It's like we're reading these. Now, how can we do that with sequences or with the? Oh, this is a better representation. I think it's with boxes. So 1 plus 2 is 3. We take the 2 and 2 is now 3 is now an input with the previous input. So 2 plus 3 is 5. 5 is now an input. Plus 3 is 8. So the output is fed as an input. So a recurrent network works pretty much like this. We have the output is fed as an input along with a new input. So remember when I fed 2 and 3 when 3 was an output? So this is the output 3. I'm refeeding it to the input. This is the same here. So the hidden state or the output here is the same as here. I'm refeeding it into the input. So this way, you'll see it in, I think, in more details in 3D. I have a 3D sketch. It's easier to understand that. So this way, can I pause this? I think I have it paused. Okay. I have the first word here, the word I. Enters, this word I enters. And I have now to predict like the next word. Or I have to read the next word. Here I will output a vector, whatever size it is. And then I will read the word like, I like. And then I take this vector and I also feed it along with the word like. So now I'm feeding the previous context with the word like to the same neural network. I take the output, which is here another vector, with the word like, I don't know, movies. And I take this output and I refeed it along as a second input with the word movie. So now this output, this vector here, captured the context of the previous two words. And so on and so forth till I reach the end of the sentence. So it's like, okay, this the blue network here is a simple neural network, one layer neural network. So in code, it's like we have a neural network here. This the single layer of neurons, and these are the neurons. First, I start by, it's like a for loop over the words. So for every word in my input sentence, I take the word and I take the hidden state, which we call the hidden state, which are the previous, which is this, the output here. The output also is also called hidden state. We call the first previous hidden state. The problem arises when we first start. So what is the input here? The input here is just a random vector, or zeros. It's a choice. Maybe zeros sometimes perform better. Random vectors other times perform better. So we start with zeros. We enter the first word. The neural network calculates some new hidden state, and this becomes our new hidden state. We finish the for loop. Go into another. We finish this one step in the for loop. We go into the other word. Again, word plus the previous hidden state equals the new hidden state. We keep looping until finishing all the words. At the end, we'll get the final hidden state is our final output. This should contain the context of the whole sentence. So sorry, this should contain the context of the whole sentence. The last representation here contains every information that we gathered from all these words. You get it? So this is how a recurrent neural network works. Just read read all the words by sequence, word by word, and then adjust your hidden state based on what word comes in. And the end, we can take this representation, slap a classifier on it, maybe another small neural network that takes as input this hidden state and outputs positive or negative, 1 or 0. And we get our prediction, and that's how we train this. A small issue with this representation here is that the word information of, okay, the information from the word what, which is the first word, doesn't influence much the output because it's far from the output. So let's say here the word what should have some, okay, it's not playing. So the word what here is in dark blue. The influence of the word what on the final hidden state is very small compared to what the influence of the last word is to the final hidden state. Why? Because when we are doing this back propagation, when we are doing this updating for the weights, since it's a multiplicative process due to the chain rule, if someone remembers it, and the chain rule is multiplicative. So whenever you multiply by a number smaller than 1, you are decreasing it. So if this error or this gradient is smaller than 1, it will decrease the way the update weights here. Here will be smaller because we multiplied by something closer than 1, less than 1. And here we are updating even less because due to the chain rule, we're multiplying by something smaller than 1. So we're multiplying by with decreasing our update weight. And at the end, this gradient will pretty much vanish, which is called the vanishing gradient function. Because if you say, like, let's take 0.9 times, or not times, to the power 20, it's a very small number. Now, if we, on the other hand, if we have a number between, like, greater than 1.1, which is which when we multiply by itself, let's say 20 times, it will explode. It will grow up a lot. So the updates on the word what will be like random updates. Like stepping. Imagine like you're stepping in a valley. With each step is 100 meters or a kilometer. Your step is very big, and then in a direction that is very, like, you're oscillating over the loss over the bottom, and you're not finding it. So this is one of the problems of RNNs, which LSTMs, which are called long short-term memory units, which are pretty much an evolution of recurrent neural network. You see it here. The recurrent neural network is simple: input, hidden state plus input, activation function, output. Done. The LSTM has much more complicated network here. It has something called forget gates and remember gates. But what I want to take from it, I don't want to delve into it. I want to say, or to get your attention on this plus here. This plus here, this addition here, breaks this chain rule, or we stop having multiplications. So we stop having exponents here. We start having additions, which have less impact on the, or will lower the impact of vanishing gradients and exploding gradients, just because we have additions and not multiplications. But at least we have an addition here. And GRUs, which are called gated recurrent units, are pretty much an even more advanced method of recurrent neural network that is easier to train on the computer. It requires less hardware and performs the same. Also, you can see the addition here. The details of the architecture, I will leave them because we're pretty much running out of time. The last slide that I have is a 3D representation of how we'll be doing this text classification problem. So we start by having this sentence. I think this slide will be the best because it will make you understand that. I have this sentence. I like this movie. So I have to start reading from, okay, first I have to transform it into vectors. So this is where I go and fetch each vector for this word. For the word I fetch the vector for it. I fetch the vector for the word like, for the word this, and for the word movie. I lay them out in the same order. And then here comes the neural network. The recurrent layer will take a random hidden state, and then we'll take the I, the vector representation of I, and it will spit out another hidden state here. And then in the third step, in the second step, I mean, we will take this hidden state here, plus the hidden, this vector, the blue vector, we input it plus the orange vector into our RNN, and it will spit out another hidden state. We keep doing that till we reach the last word. So now this hidden, or this vector here, the one in blue here, of size, we can say, let's say 300, 250, whatever. It doesn't have to be the same size as the embedding. Again, we have to choose it on our own. It's like art. I don't know. The more experience you have, the better the parameters that you choose are. So then we have the final representation of this whole sentence in one vector. What do? We just add a feed forward layer on top of it. And this layer, so this layer is connected like this. And so it's each neuron here is connected to all the inputs here. And it will spit out the number of classes, which is like 0. Like if we have a positive, neutral, and negative, we'll have 3 outputs here. And which output is the higher, it will be our prediction. It's like a probability output. And whatever output is higher is our prediction. So if you understood this, just like how this works without the math behind it, then I think I achieved my goal today. If you understood this, how this works. So we're good on this. Yes? Yes? No?
Personally, for me, yes.
تمام. السكوت علامة الرضا، يعني بعرف إنه فهمانين. Understand.
The chat will have yes as well.
Let's now take a 10 minutes break. Till 6:20, till
Fine.
6:30, till 6:30, and we'll get back at 6:30.
Okay, so everyone, we will have a 12 minutes break for the Salah prayer. And in the meantime, yes, maybe if they want to, are you going to stick around if they have any questions?
Yeah, I'm
for the
staying here. If you have any questions,
Okay,
go
so
ahead.
whoever have a question, they can discuss now with Mr. Wissam, and we will come back in 10 minutes. I'm sorry, 12 minutes. I will also distribute the attendance list.
So I'm here. Whatever you have questions, ask. Even if you don't have questions and you want to chat, please do.
Hello.
Hi.
Yeah, I joined like 20 minutes late. I've just gone through the slides and looked at what I missed. Would there be a recording that I can catch up on?
Wow.
Recording. I have to ask Miss Nermeen. I'm not sure.
Yes, we have a recording of
Okay,
whatever
yes.
from today. Yes, we do that.
Yes, the slides
Register,
are also
please, and
available.
just yes. So please register. I just posted the link for you to register.
Okay, thank you.
Welcome.
For everyone, please, this is a registration. This is attendance also for your certificates. So please click on the link and put the information. Kindly make sure when you fill in your attendance sheet, you don't in the attendance sheet you don't override or delete anybody else's information. Well, thank you. We can, I think, resume now. Do we have any special link to open for the hands-on? You're muted, Wissam.
Yeah. Go into the drive folder. Let me go. Okay. So you see my screen. Right-click on text classification, RNN blank. Open with, and you should have Google Collaboratory here. So if you don't have it, go to connect more apps, I think, and you should find it there. And it should open for you something like this. Okay, when it does, go into File, save a copy in Drive. So again, File, save a copy in Drive. It should say copy of text classification RNN blank IPYMB. So you're all there.
I think, do we have to download it and add it to our own drive?
No, when you do file, save a copy, it will save it on its own.
Oh.
So you'll have your own copy where you're editing. Now, don't worry if you're like not keeping up with me. We'll provide the solution after we finish. So if you want to just listen and watch, be my guest then. So now, select Connect. Or if you want a better computer, go into Runtime, change Runtime type, and select the GPU here. So Runtime, change Runtime type, GPU. So now you have access to a GPU processor, which is fast, very much faster. It's technically 100 times faster than a CPU to train neural networks. So now our case study here will start by. Okay, so we'll start by it's a case study on sentiment analysis on movie reviews, and the movie reviews will get them from the IMDb website. If you're familiar with IMDb, it's a website where people rate movies on a score between 0 and 10. And someone at Stanford actually compiled this data from IMDb and provided it for us with the reviews, with the stars. So to download it, you can click on play here or start, or just put the mouse or the cursor in the cell and shift enter. And when you do shift enter, it will start downloading it and will unzip it or unpack it. And you can see all the files on your left here. Wait until it finishes. So when it finishes, there will be a folder called ACL IMDb, and the folder will contain two folders. One is called train, and the other one is called, I think, validate or test. Test. Oops. Okay. So now we have two folders: train, test. The vocabulary, their vocabulary, we don't care a lot about it, and the README file that describes describes what are the files in here. So it's basically I have it here, and their citations and the reference. So each in the test set, if you open it, you'll find negative reviews and positive reviews. These are folders that contains files, and each file will have a review. And I think the name, let me just print it here. Okay, you'll see a file and then underscore the review score of it. So all positive scores have a review greater than 5. I think greater than 7. Greater than or equal to 7 out of 10. And the negative reviews, I think 4. Yeah, 4 or less. So less than or equal than 4. So I have already written here some code to go over these folders and extract the data. But first, I want to introduce you to the imports that I'm doing. The main imports that are actually important for NLP, but I didn't touch on it today, are what's called lemmatization. Lemmatization is just that it reduces the vocabulary. How? By getting the root word or the stem word from lemmatization and stemming. Sorry, it stems the word, so we only have the root word out of it all. You'll see in the examples what kind of transformation it does. So by doing that, we simplify our vocabulary. So we don't have a lot of word variation. So plurals are returned into singular. I know this isn't perfect, but this is the this is the best thing that we have. The model will score better, will learn better this way. So shift enter on this, run this cell to import everything that we need and download all the packages that we want. Also, I downloaded the stop words, English stop words. So if you want to see the English stop words, these are words that don't add pretty much any meaning to the sentiment. So it's has, hasn't, does, doesn't, did, didn't. They have negatives, but we're deciding now to ignore them. It's just a case study. It's not a perfect system. But it's easier on the model to learn. And now you can just run these cells. This cells load the positive training examples. This one loads the negative training examples. And this cell concatenates them together. So now you have one data frame that has, or one cell that has positive and negative examples. And I'm only now taking 1,000 negative and 1,000 positive. I think it has 100,000. I don't know, 100,000 whatever. But we only need 1,000 for now because we want to run it fast. 100,000 will take a lot of time to process. And we also want to do a test set. So we want to train our model on the train set, and we test it on the test set. So we know that there is no information leakage between the test and the training. So this is the best way to, not the best way, the most common way to train neural network models. Because you cannot train on the data that you're testing on. That way, the model you won't know if the model is memorizing the data or is actually learning something about word representation. It can just memorize them, and you'll see at the end how can you figure out if it is memorizing or actually learning. So now I have the testing data and the training data. So df underscore test underscore data is the testing data, and it has 100 positive and 100 negative. The positives are ones and the negatives are zeros. I think, okay, yeah, negatives, this is negatives, this is 0, and positive are ones. Why? No, can I flip them? Yes, but this is more logical. And this here I already written, this is like boilerplate code. So this is code like standard code for cleaning. This is not where I'm focusing the case study today. I'm focusing more on building the neural network, which is the hardest place. But I will go through them. So first we have a function to remove some, to clean the text, remove some special characters, which uses something called regular expressions. Regular expressions are like patterns that you can put into the text. It's more powerful than just like Control F or finding something in the text and removing it. So here I'm saying that let me zoom in a bit. I think zooming in would be better. Move this like this. Okay. I don't need this. I think this is better for you. So what does regular expressions do? This regular expression here will just go and to search for all the letters between A and Z, small a and Z, capital A and Z, and then between 0 and 9, these are the digits. And then it will include all the spaces, white spaces. So everything that is not, here I have an operator not or except. So everything except those will be removed. So I'm saying regex or regex, substitute all the characters here that are with X. Yani the characters here are everything that is not between A and Z and between 0 and 9 and is not white space. Substitute everything here with a white space. Here there is something optional. You can disable it or you can enable it. It's your choice. I'm removing digits. I could have removed them here. We can do it. It's the same thing. But this is another way. So we select /D plus, D for digits, and we replace them by a white space. And here also I'm saying take all the multiple spaces. So we might have multiple spaces after each other, and then replace them with one space. Even new lines, tabs,
Apologies, maybe he had a technical difficulty, so please bear
as
with
M.
us.
Yes.
Sorry, Wissam, you were cutting. We didn't hear the last 3 minutes, maybe 2 minutes.
Oh, sorry. What's the last thing that you heard? Upwards?
2 minutes, Tariman. We know that you talk about the regex and switching between the words. Yes, I think with the sub, yes. Before this, 2 lines before that.
Yeah, 1 second. I'm fixing the internet connection. Okay, can you hear me?
Yes, we can hear you.
Okay, perfect. I switched connection, so we should be fine now. So what was the last thing that you heard me say?
It was when you switched regular expression with text.
Oh, okay. So again, I'll go over quickly over it. Here, this regular expression will just replace everything that is not a letter, capital or small, and everything that is not a digit or white space with just it will delete it, will replace it by white space. Here it is an optional thing to remove digits. I could have done it here and just removed from 0 to 9 range, and then I won't be needing this. And the other one is just removing consecutive white spaces. So anything that's like carriage return, new line, tabs, whatever, it will be removed. Or not removed, replaced by one space, one white space. Now for the stop words, which are the useless words. How am I removing them? I'm looping over all the words. I'm looping over all the words in a sentence. If this word is not a stop word, I'm adding it. If it is a stop word, I'm just skipping it. So this function here will return a list of non-stop words. Pretty much a mouthful. Okay, so here an important thing is called the word net limitizer. So from the word net limitizer, which I think defined here up here, the word limitizer, the word net limitizer. So this will, like here, the examples here will return a limitized version of a word based on its part of speech tag. So dogs will be dog, churches will be church. Aardwolf will even I don't know what aardwolf mean, but it removed the plural form into a singular form, and you get the point here. So to do that, I have to I can either just provide it with without the POS tags, or I can compute the POS tag using the NLTK.POS, and I give it the word, and it will return back the POS tag. So this is a pretty I don't know. It's pretty hard to understand the zeros and ones here, but once you do them once, you figure them out. It's not too much important. And then I'm getting I'm doing limitizer dot limitize. I'm giving it a word plus the part of speech tag of this word. I'm doing this for all the word in a list of words. So for all the word in a sentence, I'm limitizing it. And for stemming, I already defined a stemmer and when I did the imports. The stemmer here, it's a Lancaster stemmer. There are multiple types of stemmers. So you can do, there is the Porter stemmer, regular expression stemmer, snowball stemmer. Just choose, I think Lancaster is one a good one for English. For Arabic, I think they have Iris stemmer. I'm not sure if Iris or Snowball, but there are better packages for Arabic different than NLTK. NLTK is packaged by Stanford. Was it Stanford? I think Stanford. So it has a lot of natural language processing functions ready to use, but it mainly targets English. Okay, so now that we have all our cleaning functions, this is very basic cleaning. So now that we have all our cleaning functions, we have to apply them on our text. So just first to view that, okay, I will print this. When you run this, it will print a review, and it will process, and it will print it again. It will process it into another using another function. So you'll see how the words are changing, or what is the processing doing. Remove stop words is not defined. I didn't run this. Whoops. Okay, so run this, and we have to rerun those, I think. Let's reload the frames from. Okay, everything is reloaded. So now, when I run this, first I'm removing the HTML artifacts. I'm not sure why do they have them in the text, but I removed them. Just simply replace this by an empty space. I do word tokenization. Word tokenization is that it's a fancy name for spitting on space. So I tokenize the word into you see here as, so it was as someone on space, just say space tokenization. And then after that, I removed stop words. So the word like here, who and has were removed. I'm only left with lived, and with is removed. Cerebral is here. Parse is here. For is removed. So that's it. Now I'm doing the lemmatization. Lemmatization will take some time because the loop here is a bit complicated. It's doing two things. It's calculating the POS tag and then doing lemmatization. So it's a bit slow. finished the lemmatization. Okay, it finished everything. So let's see what it did. Okay, I'm trying to find an example. Christy Brown March as reason I couldn't achieve Green Daniel. So this example doesn't have anything that got lemmatized, sadly, but it should have worked on. Does it have? No. People also do lower casing. You can do it. It's not bad. And let me do it again on the test data. Maybe we'll have something better in the test data. Okay, at the end, okay, notice that we removed all the commas, so we don't have any comma at the end. No commas. There is not much that has a comma and the apostrophe f's. Where we remove this. We can do more further cleaning if you want, like remove these single characters. The cleaning, I think, in my opinion, cleaning is the most important thing. So the better the cleaning, the thorough it is, the better the model. So can spend some few hours on this, remove those small cases, but they should improve the results. Otherwise, keep them. So now that we have our text clean, now the real work starts. So now we have to convert this list of words or convert this list of sentences into word embedding or word vectors. So first we have to start by downloading the word2vec vectors. The function here will automatically download them, or we can download them directly, grab them directly from Google, or we can use the Jensen downloader to load them. It's either way. Both of them are the same. So they will both download the same vectors. Jensen may be easier because you don't have to memorize all this line. Just api.load word2vec Google News 300, and it will give you everything. Perfect. Now it's unzipping them. So they're a bit large. I think they're. Hopefully they fit here. I think they should fit. They're 1.53 gigabytes compressed. Uncompressed, I think it's about 6. So after we finish uncompressing, we have to load these into a Jensen keyed vector object. So keyed vector are like the name is on it. The key is the word, the value is the vector. That's 300 word vector. So let's see it. Let's just finish expanding. Yalla. Okay, I think it's done. Let me refresh. Okay, it's done. It's a 3.39 gigabytes. So it's pretty large. It should fit in our memory. We have 12 gigabytes, so it should fit all. To do it, the file name was, can right-click here, copy path. Just get the file name here, and you do, let's call it wave2vec from binary. Because the file that we downloaded was a bin file, a binary file. It's called bin binary. There are other types of files. It's called a .vec or .text file. So that one will be literally the text, like the word, space, and each value of this vector will be spaced with a white space. So like Wissam, and then 100, 2, -1, 0.1, like that. But bin is a binary file. So actually, Jensen allows us to load both without not much fuss. So we start by keyed vectors dot load underscore word vec underscore format, and you give it the file name, and you also say binary equal true. Oops. So say this is a binary file, not a text file. And it should quickly load it. Now let's test those vector a bit. So if you want to get what is the closest, or what is the vector for the word monitor, so just query it like this. Word to vector from bin dot get vector, copy it from here if you want. Let's let it finish a bit. Let's do more. And it should finish in a bit. Yalla. Still loading. So here we expect the output to be 300 numbers. Because the size of the vectors are here, okay, negative 300. So we know the size is 300. And these were pre-trained on Google News. Google News is a private data set for Google. I think it's a collection of news articles from their Google search engine. So now that it's this finished, okay, we can see it's an array of real numbers, positive, negatives. Most of them are, I think, are below 1. We don't have a lot large numbers. So this is the get vector. If you get a missing vector like Wissam, I'm not sure if Wissam is in the. It will say to you Wissam, word Wissam not in vocabulary. So it has a lot of words, and if it doesn't find it, it will return this key error. We will handle it. Let's do some similarity search if you want. So let's grab the example from here. I will do word to vec dot word vec dot most similar, and we'll search about what is the most similar word. Word to vec from bin dot wv dot most similar, open parentheses, and now since we want only one word, we just provide the positive example. What is the most similar to monitor? Let's say. Whatever. It takes some time because it's now searching over all the words. So it's now comparing, and it crashed. Why? Oh, I think it couldn't load them all. So let me restart everything. So import, load. Let's crash, just run the head data. I think 12 RAM is not enough for. Don't have to run this. I have to run this. Okay, so we cannot do most similar. We want more RAM. But it should look something like this. It should print to you something like a number with the score. But we need more than 12 gigabytes of RAM because these are too much data. And we're loading, I think now. We're still processing. We have we know that we might get this issue, so we know we want to handle it. And every word that we have, we will get the vocabulary. Now we have to construct our word embedding matrix because we don't want to load all this into the network. We only want to load the words that we have in our vocabulary. So first we have to get the vocabulary. We have to know what words that we have in our dataset. To do that, we can use the from keras.preprocessing.text import tokenizer. Tokenizer will handle everything from vocabulary creation, splitting words. It will handle everything. We just have to give it our words. So we initialize it. By the way, while this is loading, Keras is a famous library for building neural networks. And I will see it. It allows you to build the neural networks like in 3 lines. So even like the word to that network will need, I think, 2 lines, 3 lines. So 3 lines will build everything, and it will provide you with the training function and everything on its own. It's very easy to use, very, I think, intuitive. And Hala, you'll see how we'll be using it. So this is finishing loading. Here, let me create an instance of the tokenizer class. So let's call it tokenizer small t equal to tokenizer parentheses. This should give me some suggestions. Let's let it finish here. Yeah, it finished. Yellow. Sorry for making you wait, but you know, we have to wait for this to finish. So I can show you what the tokenizer can take. Should be done. Okay, it's done now. And this is importing the tokenizer. And it's done. Okay. Now you can see the tokenizer class. It takes the number of words. If you want to set a limit, it takes the filter as a this is the filters here are a string where each element is a character that will be filtered. It also performs a cleaning, so you can adjust the cleaning here. It will do lower casing. It will split on the white space character. We don't. Our vocabulary is not a character level, so some people operate on characters instead of words. We don't want that. OOV token, it's out of vocabulary token. We'll keep the default for now. And document count is 0. This is all defaults. So we don't want to change anything. For later, if you want to like limit the number of vocabulary that you have, you can change this. And I want to lowercase, so everything I will keep it default. So this is the tokenizer, and I want to feed it the data. So I do tokenizer dot fit underscore on text, and I give it. Okay, now here I can give it the training data. Some people, or if you go and look out on tutorials and other articles, they will fit on all the data, the training and the testing. Honestly, okay, it will the model will perform better, but I'm against it. Why? Because you will not know the real performance of the model. Because in real life, you will train this model and you go deploy it in the wild. So people will start using it. People will use words that you've never seen in the vocabulary. And we want to simulate this thing during our training. The closer our training is to real life, to real world usage, the better is our represent. Even if the score is lower, the better is our score, or the more real our score is. So we want like, okay, we got 90% here, we go deploy, and we see that, oh wait, the model sucks. But no, we have to make the simulation or our experiment here as close as possible to real life. This is why I'm only training. I'm only getting the vocabulary in the training data. So I run this. Now my tokenizer has all the words. So let me extract the word dictionary from it. So let me call it vocab underscore dict equal a tokenizer dot word index. And let me print it. Vocab underscore dict. And also let me print the length of it. Okay, so you see the word I was mapped to 1. S was mapped to 2. Movie was mapped to 3. There was mapped to 4. we have 21,000 words. So here, since 21,000 is a small number, I can say that my embedding matrix or my input will be 28,000, which is fine. Or my vocabulary will be 21,000, which is fine. If I had like 100,000, which is a lot, I have to reduce it. So I'll take only the, I set here like when I, okay, I will say the number of words is 10,000 or whatever, 60,000, and will automatically take the most common 60,000. But here we're fine. So you can see all the words that we have. Okay, we have, if you notice, we have spell issues, but we cannot do anything about it. Okay, we can actually if we run a spell checker on top of it, on top of the pre-processing. But this is all in the pre-processing section. This is why the pre-processing is too important. Okay, now I want to construct my embedding map or my embedding matrix, because I don't want to load all this into the neural network. It's useless. I only want to load the 21,000 vectors that I have. To do that, I start by initializing a zero, an embedding matrix of all zeros. So I do embedding, let me call it embedding matrix. I use the library NumPy. So this can construct arrays or matrices for me. A matrix of zeros, and I have to provide the shape for it. A shape in a tuple, so double parentheses. The shape will be the length of my vocabulary plus 1. Can someone tell me why I'm putting plus 1 here? Someone have any idea why I'm putting plus 1? I haven't mentioned it before. That's a question. Why I'm putting plus 1 if all the words are here? Why I have this plus 1? Come on, people. Okay, remember when I said that we might have unknown words? So this is the one unknown word. Lubna, what do you want to say?
Yeah, I was just kind of wondering because in the dictionary, if we're looking at the matrix, then the indexing would start at 0, go to the whole length -1. So if you want to exclude the indexing at 0, then you would increment it by 1.
Mm-hmm. And the index at 0 will be my unknown, my unknown token.
Yeah.
Which is exactly what you said. So my index at 0 will be 0. This is my unknown token. So this is I will use this unknown token whenever I have a word that is not in my vocabulary. All right. So let's continue. So we have the first dimension here. The second dimension is 300. So we have like 21,283 by 300. It's all zeros. And then next, I want to loop over all the words in my vocabulary. So for word n, here I'm using a library called TQDM or Taqaddum, which means progress, and I'm using it for a progress bar just to visualize where is my loop in. And I'm giving it vocabdict.items. So I'm looping over all the items here. I have to say word and vec. So this will return to me the word and the value. So key and value, or word and the vector, and not the vec. Let me call it not vec. I is better because the index over all the vocabdict.items. And now, since I want to get the embeddings here, I'll go here and this, like this. Let me get the embedding vector, embedding underscore vector, equal word to vec underscore from bin dot get vector. Give it a word. the word that I'm having here. And now remember that if I don't if I don't have this word in my dictionary, this will have an error. Sorry, if I don't have this word in my word-to-vec vocabulary, I'll have an error. To handle this error, I'm using a try-catch statement or try-except in Python. So try, I'm telling it try this, except. Let's print the word which wasn't found, and let's print word not found and the word. Word not found, and let's count them. So let me initialize the counter here. Not found equals 0, and not found equal 1. Okay, now that I have my embedding vector, if embedding vector is not none, embedding vector is not none, I have to make this here, embedding vector equals none, or I can do it here, it's better. So it resets on every loop. So maybe if I'm here, and I'm now here, and I didn't get an embedding vector, I have to reset it for the next loop. So if embedding vector is not none, embedding matrix of I is equal to the embedding vector, which is here. If it is not equal to it, it will remain 0. So this comment should be here. And let's run it. Hopefully it runs. Okay, these are the words that we don't have. Morley, Haiti, inconsistencies, consistize. Okay, this is wrong. This is a spelling error. Most of them are spelling error actually. Okay, this is the TQDM. Does this? Okay, most of them are grammatical errors, but they're not much, I think. There, let's print this. They're 4015. So we have 4015 unknown words, or words that we don't have any representation for, or which are zeros. Okay. Now that we're done here, let me print this just to here. Print. Perfect. Now, okay, let's tokenize our text. So let's transform this tag, the sentences that we have, we want to transform into at least an index first. So let me tell you how this is done. So let me start by printing. What should I print? Okay. Let me take one example. So df underscore test of reviews. I'm selecting the reviews column, selecting the first review, dot split. And this will be transformed into tokenizer dot. They have the function text to sequences. And what do you give it? You give it a list. It should give it a list of text, but since here I have only one text, I will wrap it in a list. And let's run it. I think we have a space missing. Yes. Here, the word I was 1. The word C was 11. Notice that it the tokenizer performed the lowercasing on runtime. So C11 movie since I little girl. So this is much okay. Now I want to get all my my words transformed, all my sentences transformed into sequences of text. So to do that, let's do training underscore sequences equal tokenizer dot text sequence. Sorry. And I give it my training data. So df underscore training data reviews, and for the testing, pretty much the same. But instead of training, testing. Okay. Let me verify that it works. Print, let's say test, and print the training, or a test underscore, test sequence of 0. Should be the same as this. Cap 1, 11, 13, 160 order. So now we have our sentences. But there is one small problem here that might reduce our speed of training, which is that each sentence has different length. And GPUs don't like that. They like all their batch to be the same length. So if I put in the model 16 sentences at a time, the 16 sentences should have the same length. To do that, there's a function called pad sequences from Keras. It does that automatically for us. But now we want to decide what is the optimal padding sequence length. To do that, let's first visualize the distribution of the training, distribution of the length of the training data, also testing data. So let me first calculate the training data length. Train underscore length. Oops. Is equal, let's do a risk comprehension. So the 4 SN BF underscore train data. I can do it another way. I'll do it in both ways. Reviews. And length of S dot split. And print max length. So now I'm printing the max length. Or I can do it like test the score length equal the length, the risk comprehension, the length of a sequence S for S in test underscore seek. Since already test underscore seek got tokenized. So since I have a list here, I just can calculate the length of it. Which is actually, if you think about it, it's better. Yeah, let me do it. It's better than this. Maybe because we removed some characters, but it should be the same. Train underscore seek. Okay, and that's print the max length of the test underscore length. Okay, so the max length in training was 658, pretty large, and the max length in testing was 465. All right. Okay, let's now visualize the distribution, because we want to better understand that even if there is only one word with length 658. So to do that, I'm using the matplot library from Python with the PLT or pyplot package. To do that, I can do plt.histogram since I want to run a distribution. So plt.hist. And I want to plot the training length on the y-axis and the bins are I want to group by, let's see, I want to group from minimum training. Okay, wait. minimum training length to this is my range, to the maximum train length, and with a step of, let me put 20 steps. Okay, this is the range function done. The color would be red, but I want to superimpose two plots on top of each other. So red, and then density equal true, and alpha, which is the transparency, is 0.4. And the same thing, copy paste it for the test. You can highlight train and press Control D 2 times to highlight the other ones. And you go and you erase this and you type test. It's like you created 3 cursors. Control highlight, Control D, and then start typing. And plt.show. And this should be blue. Okay, this is pretty much they follow the same distribution. So almost all our reviews are like under 400. Most probably 90% of them under 400. So we can let's check if we selected 400 or 300, what will be the how many words will be missing. So let's set the maximum length to 300. Again, this is very important because analyzing your data set like this will make you understand better what parameters to choose. Like how will I choose the maximum length here? Because I plotted this plot and I noticed that most of our data is under 300. So print, and then I want to print. Okay, I want to check how many sentences are longer than 300. So to do that, I'm going to sum up the list of x greater than max length, score length, for x in train underscore length. So if x is greater than max underscore length, it will be true. Then I'm summing it up. So sum of 1, I'm counting how many sentences greater than max length. The same for testing. And let's print. Okay, we have 159 sentences out of 2000 and 11 sentences out of 200. Which is okay, good, a good number. If you put 400, 65 by 6, but 400, like think of it as you have more sentences with padding at the end down, and the training will be slower. So now, just for the sake of time, I'm doing maximum length of 300. But there is more advanced ways to do this padding, and you do it on a batch level. So, okay, let me introduce the concept of batches. And when you train a neural network model, you have to to run this data inside the neural network, and then you want to backpropagate. When you do backpropagation, you have to calculate the errors for all of the values. Remember, you were calculating the weight updates for every weight in our matrix. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 weights for this simple matrix. Imagine if you have 300 here, it will be very large. So the data the network won't fit on the GPU with multiple examples. So what we do, we select only a sample of the examples, so like 16 or 32 or 64 ones, and we just do an update based on those samples that we took. This is called the stochastic gradient descent. Someone, I think, asked a question. Oh, type in chat. Oh, okay. That's fine. So that's why we need batches. So we feed our data in batches and not fully. We don't throw it all on the GPU. So when we do it in batches, there are ways to pad the sequences while batching them. So we only select, we check what is the maximum length in this batch, and then we pad only this batch. We don't pad the whole arrays that we have. This is another way, but this is a bit more complicated for Keras. So I'm just so you know how we can do it another way. But this works. This works. The other one will probably improve the speed a bit, the speed of training. So let's pad our sentences. So let's call them training underscore sequence underscore pad is equal to pad sequence function that we defined here, that we imported here. So whoops, pad underscore sequences, and this takes as input the sequences. It takes the max length, equal to max length. Data type integer 32, yes. Okay, now we have to choose the padding. The padding can be before the sentence or after the sentence. Now let me here ask you a question. Let me show you which example. This example here. Which is better? Putting the padding on the left or on the right? What do you think? So, putting the padding on the left or on the right? Padding is just a pad, a token here called pad. It has no meaning. It's all zeros. The model will learn that this has no value. But we should put it on the left of the sentence or on the right of the sentence. There's 50% chance you get it right. Nermin, put it on the right. Well, you can, but it's suboptimal. Why? Why? Because remember when I said that the model has to read from left to right here? Okay, it read the what time is it? Question mark, and then it has to read pad. Okay, pad, I have to learn to ignore it. Pad, I have to learn to ignore it. And then when I do gradient updates, or when I do my gradient updates, I have to go through all this padding again, and then go into my what time is it. If I put it on the left, I will read through this bunch of useless data, and then I got a word what. Now this what is closer to the end than if we had the padding on the right. So this way, the training will be faster as in we will reach our accuracy faster, just because we put it on the left. Now, some people suggested that we can do something called a bidirectional neural network. What does it do? It's bidirectional means that we have two neural networks, one that goes from left to right and one that goes from right to left. And this way, each we can put a padding on its own data for. Each will have its own data with its own padding, and this way we'll like read the sentence from the left to the right and from the right to the left, and at the end we'll just concatenate these two representations here, the blue ones. We'll just take them, stick them together, concatenate them together, so we get one larger, like it's double the size of 300. It's 1/600 vector. And we'll do classification on it. I think in Keras, it's all this that I talked about is just one line. So let me go. Okay, I went on a tangent here. So let me get back to my padding. You can do post or pre. I will do pre. I think the solution is post, but who cares? So okay. What do we have more? Truncating. So maybe if the sentence is longer, what we have to do? We have to cut it. I think cutting from the end is better, because usually humans start the gist of their review, or the sentiment in the review will be most probably be in the first few sentences. So I will leave that truncating. Oh, I have to change it. So truncating equal post. And what do we have more? Value. What is the value here? float or string, the padding value is to 0. Yes, we want it to 0. Perfect. Raises. Okay, we don't care about this. We have to do the same for testing. Again, highlight, Control D, write test. Sentence. Okay, now we have them padded. Let's examine the first one here. So you see 0, 0, 0, 0, and we started. 13, 2 to 5, 2, 8, 4, whatever. So we're good here. Now, text preprocessing is done. We have our IDs. We have our embedding matrix here. Embedding matrix. Now we need to construct this model. To construct this model, just like a builder, I will start building the embedding layer. I'll slap on top of it the recurrent layer. I'll slap on top of it the feed forward layer, and at the end I will get the number of classes as output. So to do that using Keras, it's very easy. From Keras, import the layers, the models, and the optimizers. Optimizers are the one that will do the gradient descent and everything for us. And I want to import sequentials, which is I want to construct the model as I'm speaking, like from bottom to top, or in a list. You'll see what I mean. So first I have to define my model. Model equal to sequential. Let me run this first. Model sequential. Does it take anything? Okay. And you see here how will I do it? I will do model.add. Here is TensorFlow. Just ignore this. Keras.layers, but I already have the layers. So layers.dense. Layers. You'll see how I do it. So first I need the embedding layer. So model.add. Open brackets. The embedding layers, I can get it from layers. So layers. It will open to me all the layers available for me. And I will select embedding. Embedding. Okay, embedding layer takes multiple parameters. The input dimension. The input dimension is the length of my vocabulary. So it is length of the vocab bit plus 1. Don't forget the plus 1. Okay. Let me put it into variables. This is so you understand it better. Input underscore dim equal here, comma, output dim. What is the output dimension here? Can anyone help me? It's one number. If the input is the vocabulary, the output is where's the picture? Where's my output here? If the input is 600, the output is if the input is 60,000 or 28,000, the vocabulary size, the output is 300. So now here I have 300 because my embedding length is 300. And since I already have embeddings learned, pre-trained embeddings, which are the embedding matrix, I just provide them here, embedding matrix. If I don't do this layer will initialize the embeddings to random numbers, and it will learn them as it goes. See my point here? So I don't want to do that. I want to benefit from the information learned in this word-to-vec embedding. I want to benefit from this information and build on top of it. I don't want to learn it all from scratch. So this is why the word vectors here are important. If I don't do this, the performance will drop drastically. So what I have to do, mask. Okay, what do we have here more? I think mask. Activate, don't care. Mask 0. Index 0 cannot be used in the vocabulary. 0 should be the embeddings, the padding matrix or the unknown. So mask underscore 0 is equal to true. The input length, maximum input length, it's better to provide it so the model knows its maximum length. It usually doesn't care. It expects to learn it or to get from the batch. But we can include it. No harm in it. What do we need more? Okay. Here there is a parameter called trainable. Trainable. Not sure why it's not highlighted. Trainable equal false. Why am I like freezing this layer? I'm freezing this layer because I don't want to change those embeddings. Why? Here you can do two things. Either you continue training these layers, you continue to update those weights, or you freeze them like I did now. If you continue updating them, let's say now you got the word I don't know, you got some word in this cluster here. Let me get a cluster here, and you change the representation for the word cold. The word cold now is here. It's farther from warm and hot for some reason. But now you never seen the word warm and hot in your small training data here, so you didn't update those. Now when the classifier comes in and okay sees this representation here, okay, he knows how to classify cold as being, I don't know, negative maybe. Let's say, for example, negative. But it doesn't know how to classify warm and hot because they're farther away. So what if we freeze those, we keep those untrainable, we don't touch them. So if it learns the representation of the word cold, it will also learn the representation of the word warm and warm. So if it knew that the word مثلا, for example, the word cold is negative, it will also learn that the word warm is also negative and hot is negative. This can be good and can be bad at the same time. So we also have to choose here if we do it positive or sorry, if we do it false or true. But since we don't have a lot of data, it is recommended to keep it false, to not train it. So now we added the embedding layer. I think there is a parenthesis missing here. This slide. Yes, two parentheses at the end. Oh, there is one extra here. Sorry. Now it is correct. Okay, I added my embedding layer. Now I have to add my recurrent layer. To add my recurrent layer, model.add layers. Here I have multiple types of recurrent layers. I have my simple old RNN. I have my LSTM. I have my GRU. You can use whatever one you want. I'm choosing the LSTM because I'm confident that this is better. Sometimes GRU is better. Let me take GRU. It is functionally the same. It will take the same inputs. So I will say to it, units equals 300, which is I'm now defining what size the representation here should be. Even if here it's 300, I can put here 250. Like it's like compressing a bit those representation. I can put it 600. How do I know what to put it on? I don't. If I knew, I would be a millionaire. But I don't. This is $1 million question. So let me put it like 256. Let's say arbitrary number. After my GRU, after my recurrent layer, I need to add my feed forward layer, which is my this green layer here. This is my classifier layer. So this takes as input the features from the recurrent layer and classifies them. Oh, it prepares them for classification. It's a better term. So layers dot dense, called dense layer here. Why dense? Because all these are connected. If you look at here, all these are connected to all the inputs. Every input or every neuron is connected to all the inputs. This is why it's called dense. So imagine if you have 300, that will be a forest. So dense, let's say the size, units equals, I don't know, 400. Maybe not 200, I think it's better. Maybe, I don't know. And the activation is called ReLU. I haven't touched on activation before. Let me show you a bit what ReLU is. ReLU activation. This is the ReLU function. If the output is less than 0, then the output is 0. If the output is greater than 0, the output is the same. This is the ReLU function. This is one activation function. There are more than one. We have the sigmoid one. And if the input is this like squashes everything between 0 and 1. We have 10H. We have leaky ReLU, which is like not 0, totally 0, a bit less than 0. There are multiple activation functions. One of the most popular is ReLU or leaky ReLU. Each one has its advantages and disadvantages. Right now we're using ReLU. We're just beginners here. Again, you can change it with one literally one string here. And then at the end, I want to add my final output layer. So I will say model.add layers, also .dense. And since I only have positive and negative, so I have two, but I can do, if it's greater than 0.5, it is positive, less than 0.5, it's negative. So I only need one neuron at the end. So units equals 1. And activation equals to sigmoid. Why sigmoid? Because I want, where do I have it? Do I have it as sigmoid? Let me show you the sigmoid. Sigmoid crushes everything between 0 and 1. So if my my output is greater than 0.5, it is a positive. Less than 0.5, it is negative. And whatever the input was, like here, if the input is -6, it will still be squashed between 0 and 0.5 using the equation here. It's 1 over 1 plus exponential minus z minus the input. So here we're done. Let's print the model summary. Model.summary. Did it work? Yes, it did. So the input is, here it says none, but we know that it is length of vocab plus 1. Oh, this is the output shape, not the input shape. So the output is 300 by 300 because we have the maximum length of 300. So if I had this 250, it will be here 250. So output here will be 250 by 300, which is the number of words by the embedding vector size. After that, the what's it called? The RNN. Where's this slides? The RNN will go over all the words and will spit out one vector, which is here the 256 vector, 256 a vector of size 256, and this vector will be fed into the feed forward layer. It will spit out a 200 a vector of size 200, which will then be fed into a final dense layer, which will spit out one value between 0 and 1. The none here is the batch size. So if I have my batch is 16, it will be 16 by 300 by 300. Okay, I have okay. My total parameters are 6,800,000, but my trainer parameter are the sum of these, because this I didn't touch this. I don't want to train this. So now the function or the model should train fast. To train, I have to compile my model. So I do model.compile. I have to specify my optimizer. There's one called Adam. It's a variation on gradient descent, which is back propagation. It's also a variation on back propagation. I have loss. My loss is binary cross entropy. Binary cross entropy basically, think of it as comparing the output. It basically compares the output with the true label, but using some probabilities and logs. I'm copying it. Cross entropy. And my metrics. Oh, we didn't touch on metrics this time. I want to track the accuracy. So how good is my model? Did I do something wrong? Yes, this is it. Come. So this is my model now. And how to train it? I can train it using the .fit function. So I want to collect my history. So model history is equal to model dot fit, and I give it X is the training data. So training underscore sequences underscore pattern. Y is the labels. Our labels are the zeros and ones from the beginning, if you remember. So df underscore training data of on labels. And the validation data, which is the testing data. Here the validation data is a tuple, so I should put test underscore sequences underscore pad and df underscore test data underscore brackets labels. Oops. What do we need more? Okay. Oh, there's a parameters called epochs. Epochs is how many times we want to loop over all the data, how many times we want to feed all the data all in together. Let's put it at 10, or let's put it at 5 here, just for the sake of time. And we want to shuffle. Each epoch, please shuffle the data. And if you want the batch size, you can set it here. If you don't set it, I think it defaults to 32. 32. Let's put it 32. And let's start training. So this should run fast, I think. First epoch. Okay, it takes 50 seconds per epoch. It should look like this, but instead of LSTM, here it should have GRU. It should start here. I think I did a training on 25,000 instead of 1,000. Here it's doing on 63. On 63 because of batch size. So if you do 63 times 32, it's 2,000. So we have 2,000 training instance, which is right. Actually, the last one is half a batch, but it's fine. So, okay, right now we're finishing the first. Okay, you can see the loss and the accuracy. The accuracy is improving, but this is the training accuracy. The training accuracy, okay, we care about it, but not much. We care about the validation accuracy. So the accuracy on the validation data. Here something weird happened, but it usually sometimes happens. The validation accuracy is greater than the training accuracy. But this should normalize when we continue the training. So let's keep it running. At the end, I will plot the accuracy and the validation accuracy, and I will show you what do we mean by overfitting or underfitting or maybe memorization. So now, okay, our accuracy started growing very fast, our training accuracy, because I think here the model started memorizing the training sentences, because this is the second time it read them, not the first time, it's the second time. The validation accuracy should increase a bit, but not as much as the accuracy here. It increased to 83. This will keep increasing till it reaches 1, but it doesn't mean that we have a 100% accuracy. It means that we memorize the training data. So let's keep it. Let's wait for it to finish. And I think here when we include more data, the performance will be much better, because we included more samples that the model will train on. Like here we reached 87% accuracy. I don't think here we will reach 87. Let me see. I doubt. Let's see. Okay, accuracy here, notice the accuracy started dropping because we started only memorizing and forgetting about the general or the most important features. So let me, I have a solution notebook here. I can show you what this can look like. You will not get the same one. Each one, I think, will get a different representation here or different graph. But you see here the test started flattening out and the training kept increasing. This here, when this happens, this is overfitting. So the model is overfitting the training data, or the model is memorizing the training data, and it is not anymore learning. The more training data we have, the less the memorizing is, because it cannot like memorize 50 gigabytes of training data and 300 megabytes model. This it's like a compression thing. I don't think I will be able to catch on how we do a prediction, but I have it in the solution here. You just provided model.predict and you provide it with the sequences, the text sequences, and it should print out something like this. So 0.99, 0.99, 0.83, which is positive. Or I can do model.predict classes. Predict classes will, by its own, just apply a threshold. So greater than 0.5, it's 1. Less than 0.5, it's 0. And we can feed it into something called the classification report. This function, we feed it the labels, and we feed it the classes. It will give us the accuracy, and it will give us the other metrics, which are F1 score, recall, and precisions, which are more important if we care about. I'm not going to touch on them. We have only 10 minutes. But if we don't have balanced data, so here we have 100 by 100, positive, 100 positive, 100 negative. Maybe we have like 1,000 positive. Imagine like cancer research. You have 1,000 negative cancer patients, and you have 100 positive cancer patients. If you predict everything is negative, you have 90% accuracy. But you're dumb because you don't care about the accuracy. Here you care about your precision. Because I need to catch those small patients. I need to catch those patients that have cancers. I don't need to catch. I care about. Okay, it's more harmful to tell positive cancer patients that he's negative than telling a negative than telling a positive negative. Sorry, patients with no cancer that he has cancer. If I tell him that, he will go and make another exam. Just like PCR and COVID, the precision here, when they say the precision, it's this number when they tell you about how precise is the PCR test. So the more the test is precise, the more accurate it is on detecting positive cases. So these numbers we should care about in real life. And at the end, you can predict the labels for all the cases that we have. Here, is it finished? Did it finish? Oh, I think it's finished. So let me copy those and I will run them. I will run them as they are. We don't have time to write them. Okay. Copied.
Sorry, we have a request here. If you can share the solution notebook.
Yes, I will put it in the same folder when I finish. So run it on. Here you see the predictions that are different. Like I predicted one negative. Let's see the classification report. 81% accuracy compared to 83 before. Predict on all the classes and gather the wrong predictions. And let's see what were the wrong predictions. Let's see one. So, Malcolm McDowell diagnoses daughter from illness, believes. Okay, here it's broken English. But this was, I think, I forgot what the review is. Let's see the label. Oh, sorry, of 11. It should have been positive. We did it as negative. The model classified it as negative, maybe because it saw illness, it saw it's negative. So this you should examine the wrong predictions to understand your model's behavior. After that, if you want to save your model, just do model.save and we usually follow the .h5 extension. Just so you know that it's an H5, it's a model by Keras. And if you want to load it from Keras.model, load model, and you'll get it from the saved data. And this is how we conclude our session today, our workshop today. If you have any question, if you have anything, we have, I think, 5 minutes left for questions. So, yeah, go ahead, ask me. On the slides, on the code, I will share with you the notebook. I will upload it to the same folder as we speak. Make a copy. If you're interested, guys, there's a competition now going in Saudi Arabia. It's from the Coast University, I think. It's the biggest sentiment analysis competition in the Arab region. I think they have. It sounds like I'm doing NLP, but it has. I think they have 555,000 examples, positive and negative and neutral. And the prize is, I think, $10,000 for the first, 5,000 for the second. So sign up here, you can test this model. There is a public leaderboard. I'm this, okay, I should be the second. Okay, today I'm the third, but the stakes are close to each other. If you use this model that I gave you, I think you should score somewhere. It should be, you should be able to do greater than 60%. I'm not sure. The other ones are using more advanced transformer models. I just gave my secret away, but they're using all transformer models, which are a bit more complicated for us now. But this is, I guess this is a good exercise because you get to see how is the data, how can you clean the data, and how to improve your model. And I also might be using this model in the competition. Might. So yeah, if you have any questions, go ahead. I hope you win. I hope too. Thank you, doctor. Thank you.
We thank everybody, and a big thank you to you, Wissam. Really, we enjoyed this amazing workshop and presentation. Mashallah, very informative, and we appreciate all of your effort. And we thank everybody for coming and attending. And we hope that you enjoyed it as much as I personally did.
Thank you, everyone. Thank you, Nidmi, for hosting this session.
So for everybody, we'll keep you informed for any future events, and thank you all. Okay, we'll see you. Yeah, bye bye.
Yeah, bye bye.